In the following pair of videos, I want to discuss the phenomena of osmotic pressure, which is something that you may have discussed in your Gen Chem courses, but now that we've developed a quantitative framework for studying mixtures, I want to use those same tools for doing a rigorous and thorough analysis of what osmotic pressure is. And so in general, just to explain it in words, osmotic pressure is a phenomenon that describes flow through a solute through what we call a semi-permeable membrane. And so what I mean by that is it's essentially just like a wall that filters some species through. So it's a wall that lets some things through, but not others. So that's just a very general way of thinking about it. And the reason I want to bring up osmotic pressure, or that it's important to discuss as chemical engineers, is because it's a phenomena that affects many aspects, many different types of systems. And so, for instance, osmotic pressure is very important for understanding biology because many of the ways that our cells in our body or in many other parts of nature, many of the ways that cells interact with one another is by using osmotic pressure as their means of communication. Furthermore, osmotic pressure is also important if you're considering increasing access to different water sources. And so, for instance, in the desalination plants, in the south of Florida, all of them, operate based on, manipulating the osmotic pressure through a membrane. Okay, and also there's increased interest in using polymeric hydrogels to clean up pollutants in our ocean waters as well. And the way that these hydrogels work to absorb or pick up these pollutants is through the phenomena of osmotic pressure. Okay, and so these are various different applications of osmotic pressure, but to at least discuss it and to build a physical intuition for you, what we're going to consider is the following sort of experimental setup. Okay, and so consider that we have this vessel that's split into two compartments. So on the left-hand side here, we have what we call the alpha compartment, and on the right-hand side, we're going to have the beta compartment. And then in each compartment, we have these little two stems here. Okay, and in the middle here, this is where our semi-permeable membrane is going to be. Okay. All right, and so at the beginning of this experiment, let's say that both the alpha and the beta compartments are just filled with pure solvent. Okay. And they're at the same level, right? Okay, and you could think of this solvent as being like water or something. In any case, both of these compartments are filled with the same solvent, and they have the same sort of atmospheric pressure acting on them. And so we'll call that P naught. Okay? All right, and so if we think about what the chemical potentials of each compartment are, so alpha, and we'll say that, so both of these are going to be equal to our standard state chemical potential, right, which is for the pure species. And so U alpha is equal to that, and U beta is also equal to that. Okay? All right, and we'll also say this is for the solvent, which we'll call species 1. All right, so that's the initial setup of the problem. But then, let's say at some instant of time, in compartment B, we spike it with a small amount of solute. Right? And let's say this solute is something that can't pass through the membrane. And so some examples that you could think of would be, maybe it's some type of salt, or it could be a bigger molecule like a protein, or even a polymer chain. Okay. In any case, it's something that can't pass through this membrane. The membrane has holes, and the solute is bigger than those holes, so it just can't fit through. Okay. In any case, when we do that, when we add solute to the beta compartment, we're going to change its chemical potential, right? And so instead of being just equal to the pure species, it's now going to have an RT-ln of X1 term there, where once again this X1 refers to the solvent. Okay. Now this is important because even just mathematically, we know that the mole fraction is a value that's less than 1. And so, if we have something that's smaller than 1 inside the natural log, that makes the natural log negative. And so this term here is negative. And so, if this is negative, this will subtract off the pure species chemical potential, making mu1 beta less than the pure species chemical potential. Okay? At the same time, the alpha phase, we didn't do anything to that, so its chemical potential is still equal to the pure species chemical potential. And so what happens by adding in that solute, what ends up happening is we make mu1 beta less than mu1 alpha. Okay? And so if we disturb the relationship between the two chemical potentials, right, we end up making the beta chemical potential lower than the alpha chemical potential. And so as a result, the system now has a driving force, right? Because the driving force is that both of the chemical potentials for each compartment need to be equal to one another. Okay? So now the alpha phase and the beta phase, now there's a difference between the two. And so now the system needs to react and do something in order to get those two chemical potentials back to the same value. Okay? Now here's where that semi-permeable membrane becomes important. Okay? And so we have this concentration of solute here, right? And normally, like you learn in your transport phenomena class, if you have a high concentration here, it's going to want to diffuse to a lower concentration. But this wall is in the way. Okay? These solutes can't fit through the wall. And so they can't really move to the other side. So if the solute is stuck here in the beta phase, but the solvent can move freely through that wall. And so what ends up happening is if the solute can't move to the alpha compartment, what we're going to see is that the pure solvent is just going to move to the beta compartment. So we start to see pure solvent flow this way. And it's flowing from the alpha compartment to the beta compartment because it's trying to equalize out those two chemical potentials. Okay? So we start to see solvent flow from the alpha to the beta compartment. And so as a result of that, the liquid levels between the two compartments will start to change. And so the liquid level in the alpha compartment slightly decreases, and the liquid level in the beta compartment increases. Okay? Alright, and so because the chemical potential in the beta phase ends up being lower than the alpha phase one, we see solvent permeate is the word, permeate into the beta side. Okay? And so essentially what this is trying to do is it's trying to dilute the concentration of the solute in the beta side so that this x1 term for the beta side starts to increase and go towards 1. And once you have a natural log of 1, that's going to be equal to 0. And then you would get back the pure chemical potential value. Okay? So that's, physically what's going on. Another way we could characterize it is, let's say, we have this solvent flowing from the alpha to the beta side. And let's say we wanted to stop that flow. Okay? All right, and so essentially, once again, we have liquid flowing from one side to another, right? And so in order to stop flow, or whenever you think of liquid flow, you should always think of, pressure differentials, right? And so if we wanted to stop the flow of liquid, what we would have to do is we would have to apply some sort of pressure against that flow, okay, to somehow stop it. Okay, and so the way we could think of it is, let's say in this little stem here, we put in a little piston cylinder. Okay, and so we put in a piston cylinder system where we could apply a force. And when we apply a force, we're essentially, what we're doing is we're changing the pressure on the beta side. Okay? And so let's say we apply a force so that our new pressure is P naught plus what we call pi, right? And let's say that that new pressure is enough to stop the flow of solvent from the alpha compartment. Okay? So to stop flow, can apply pressure on beta side. Okay? All right, and so this new pressure, or this pressure differential between, the original atmospheric pressure and our new pressure, is this pi value. Okay? And that's what we refer to as osmotic pressure. And so osmotic pressure, which we abbreviate as pi, is essentially the pressure needed to stop flow of solvent. Okay? Okay? Or another way to think of it, so when the system reaches both mechanical and chemical equilibrium. Because remember, mechanical equilibrium is when the pressures on both sides are equal, and then chemical equilibrium is when those chemical potentials on both sides are equal. Okay? Or another way to think of chemical potential is it's just the another way to think of osmotic pressure is it's the thermodynamic drive to dilute the beta phase, to make it as close to pure solvent as it can be. All right? And then experimentally, when people have studied the phenomena of osmotic pressure, they've observed that osmotic pressure is about equal to, or approximately equal to, the concentration of the solute times RT, for the case where you have dilute concentrations. So this is specifically the solute concentration.